think some gods are worse at mathematics than others, so I don't know. So just make sure you're praying to the correct God if you want math help.
I was going to say, Zeus is pretty good at multiplication.
Yes, that's true. Infamously good.
All the kids these days.
Okay, enough about the mating habits of the various gods. Never taught that during calculus. Okay. So first thing I wanted to see, it's been a while. If anybody has any, are you out? You're almost, there's one mask. Does anyone have anything from homework that you have a question about? Or just generally? What's going to be a good location? I think this is good. Really? Okay. No? All right. I'm a little surprised. There are some really weird homework questions. So it's not just you. If you're like, that is really weird.
I mean, math got weird when you put the alphabet in it.
Oh, please. Enough of that stuff. Now, if there's no questions, okay. Let's do this. I want to make sure about a couple things. Can somebody remind me what, if I have, holy crap, that G went crazy. If I have G of X is natural log of X, what is G prime?
1 over X.
1 over X.
times, no.
A lot. One thing I want you to realize, and how do I rewrite this? Isn't this x to the negative 1? Yay! Right? So here's a little side note, if I start out with x squared, what's its derivative?
2.
What's that guy's derivative?
2.
And what's that guy's derivative?
2.
And then what's the derivative forever after?
0.
All right. Can I get from the positive exponents to the negative exponents through differentiation? Does that make sense? I can make my exponents go down in degree, and then it gets to 0. That stops. It doesn't get to negative. So what's the bridge to get to negative exponents? Natural log. That's just the way I kind of was like, oh, that's how you jump from one side to the other. Okay, maybe. So let's combine a few things, because that's what we like to do apparently. What about this here? Tangent of the natural log of cosine x. Yeah, take that away. You need more room. I got all kinds of weird shit going. Not as good as I thought you were going to be. All right. What's going on here?
Function within a function.
Function inside of a function inside of a function. Russia nesting dolls, right? What's the most important function up there at first?
Tan X.
Tangent of stuff, right? What's the derivative of tangent of stuff?
Secant squared.
Secant squared of stuff. And of course, we understand that we don't just stop there. What do I have to do then? Multiply by
The derivative of stuff.
the derivative of stuff. Good Lord, Jeff, come on, dude. Now, I desperately want you to understand. Real quick side note, don't even write this down. If y is tangent x, what's y prime? You already told me. Secant squared x. Times the derivative of the inside. And what's the derivative of x? So we are actually always doing chain rule. We're always doing it. But the way we teach it, we sort of say, the inside is just x. It's not going to show up. So it gives a shit, right? We don't have to even think about it. But I want you to realize it's just always there. Okay, so now, and the thing about chain rule, I know a few of you guys are still having trouble with chain rule. Do you see what I did here? All I did was the derivative of tangent stuff is secant squared stuff. And then I put times this. I'm not worried about that yet. Now I keep going as if this is a brand new problem, as if this is the problem I gave you, right? I know that kind of sucks. It could have been better, but this is the problem you got. So this is just sort of done. It's just waiting. Good Lord, Jeff. That is a parenthesis. What about this?
1 over cosine x.
Yeah, the most important thing is this natural log of stuff. Derivative of natural log of stuff is 1 over stuff.
Derivative of cosine x.
Derivative of cosine. What's up, Thomas?
I'm trying to remember the identity of whatever the cosine is.
Oh. Bless you.
What's
There you go.
secant?
Secant.
Yeah.
Yeah, C goes to S, S goes to C. Sine goes to cosecant, cosine goes to C.
Basically flip it, give it a go.
So, what's the derivative of cosine?
Negative sine.
And what's negative sine over cosine?
Negative
Negative tangent. So I can write this as negative tangent x, secant squared, natural log. Jeff, cosine x. Second, this came from this, right? Yes.
We just got to like the second to last part on a quiz or test where we marked
Oh, if you made this negative sign, there's a few different things. Thomas, if you would have put secant here, you could have had secant squared this times secant x times sine x and put a negative out front. I would have been okay with that, right? You guys with me? So I would have accepted answers that don't end up with tangent, but you have to do some basic simplification if you see it. So yeah, if you made that secant and made that negative sign and didn't realize, and you just left it there, you're fine. Yeah. Okay, I locked it. Some of you guys are really being very loose with your parentheses. So are these two things different?
Yeah.
Yeah, right. Okay, so just, very often you're your own worst enemy. I didn't make the problem that hard, you did, right? Because you kind of rewrite it wrong. You kind of don't write it the way I wrote it. You sort of imagine parentheses are there that aren't really there. That happened a lot on that, I can't remember if it was the last quiz. You're not going to remember. Oh yeah, number 2 for some reason. People were putting parentheses in, making the whole problem worse than it's supposed to be. I mean, it wasn't supposed to be pretty. Are you guys all right? So some people, it was 3x sine x minus 3 pi squared. And some of you guys were writing this as if it was 3x sine, no, it was this. Oh my God, not that, just crazy. That's terrible. I didn't do that. That's not the problem I made. I don't want that problem. I like that problem. And whoever got some of you guys got the right answer. It's actually a really nice little tiny answer, right? It doesn't seem like that gross thing, but anyway. I don't know, guys. It's chain rule is not. It really isn't necessary to do a lot of side work, but it's not bad to do some side work. I know some people do they put the outside function and then they put the inside function and they do some derivatives. I mean, there isn't anything too wrong with that, but is this anywhere in there? Is this in there? Is this in there? No, it isn't, right? So just gotta be careful what you mean when so when you write this, you really mean tangent stuff. I don't know. I'm trying to help you guys. I really am. Chain rule can be one of the most difficult things to get down. And I really never understood that, to be really honest, until I saw some ways that some teachers teach it. Like you have to know ahead of time. Did I know ahead of time how many? I didn't have to. Just every time I did the derivative of the inside, then I worried, oh, there's an inside again. And then when I get here, no more insight. I'm done. I can see in some of your eyes you have a moral dilemma. You're like, I kind of wish he was still sick.
I'm kind of wondering, are you okay?
Why? What's up?
You have a mental breakdown whenever there's a difficult concept.
Mental breakdown? Hopefully not. I don't think I've had a mental breakdown in front of a class yet. I don't know. It's always the first time for something. Now. Let's see. What else was it? Oh, one other thing. We haven't talked about this yet. Log-based data. I know what the derivative of natural log is. But now I'm curious, what about log base 2? What about log base 11? What about log base pi? Do you guys know log base pi exists? Did you want to know?
I know it exists.
Understood. You can't unhear what I said, though, too bad.
You got me.
So let's do this the long way. To investigate this. I'm going to bring y back. Right? Jeff is bringing y back. How do I rewrite that? How do I rewrite from logarithmic to exponential?
A to the power y.
Yes. A, that's the base, correct? And the answer to a log is the power. The answer to a log is the power the base needs to become this. Yes, yes, yes. So again, what's log base 2 of 8? 3, because 2 needs a third power to become 8. So I can always rewrite from one form to the other. Okay. So this becomes a to the y equals x. A to the y equals x. If I wanted to take this guy's derivative, what process would I have to use? Implicit. Because now I've got a function of x that's inside of it. Right? Oh shit. I love you guys. So I can't read you today. I didn't know what I'd be like today. What's the derivative of a to the y? Just to remember, recall.
Y a to the y.
No. What's the derivative of 2 to the x? What's the derivative of e to the x? E to the x. What's the derivative of 2 to the x? Come on. You do it.
Natural log 2 times 2 to the x.
2 to the x, natural log of 2. I think of this as the adjustment because that's not e. So this is going to be, I don't know if you guys, I'm going to say, it's going to be cool at the end. You're going to see a nice analogy happening. All right, in your house. Believe it when I see it, Jeff. So what's the derivative of a to the y? A to the y, natural log of y, times, it's not x, right? It's y.
Y prime.
Y prime. What's the derivative of x? 1. So I get y prime equals 1 over a to the y natural log of y. Why y, Jeff? This should be 8. I'm being silly. Natural log of the base, natural log of the base. Is that cool? Natural log of the base. Let me stop for a minute. So this is what we did before. The minute we learned implicit, we could go hit these functions that we had no idea how to do their derivatives. We didn't want to do limit definition, right? But with implicit, we could rewrite it in a form, oh, I know the derivatives. And I do the derivatives, and then I kind of solve again. So whenever we learn a new process like implicit, we're learning a new way to kind of shortcut the limit definition. Use derivatives we know to find derivatives we don't know. So somebody help me out. What is a to the y? X. And what is ln a? ln a. So if I have log base a of x, the derivative is 1 over x ln a. What if it was log base e, natural log? Was there a natural log of x? We said this earlier, derivative of natural log of x. Don't overthink it.
1 over x.
1 over x. And isn't that exactly what would happen if the base was e? Yes, yes, yes. So that's kind of nice. Again, when I'm doing an exponential, the adjustment is times. This is an adjustment because the base is not e. When I'm doing a logarithmic differentiation, the adjustment is divided by. This is an adjustment because the base might not be e. Okay. All right, so that was one little thing that was left over from the logarithmic section. Now, you're really going to want to, if you haven't yet, watch the video that I posted in Canvas. Well, let's do a couple of things. All right, let me just tell us. When you took algebra, what section were you most dreading? Anybody remember? Or when you took pre-calculus, what were you most dreading to happen?
All of it?
No. Pre-calc, no trig. Sorry, I heard somebody. No? I mean, come on. Every student's worst, most hated thing.
Word problem?
Word problems, right? Isn't that you? Or no, are you guys a group of guys that love word problems?
Oh, no.
That'd be so cool. All right.
Well,
Normally,
so,
students despise word problems. And part of me can understand because very often the word problems are really dumb. Fred put money to 2 accounts. He can't remember how much money. Who the shit is this guy? So much freaking money. He's like, I forgot how much money. So part of your brain probably when you see some of these dumbass word problems that have been created, you're like, when is this going to happen in real life? That's why I love that thing about Sally with the 60 cantaloupes. You go buy 60. I don't know if I put that on your. There's a little thing I like to do on my syllabi for some classes. Only in math can you buy 60 cantaloupes and nobody asks what the hell's wrong with you.
Oh,
Did I
yeah.
put that on this? Yeah.
There's actually a couple of pictures circulating around the internet of some guy who actually filled his entire truck with watermelons.
Oh, there you go.
Yeah, the only title to any of those pictures is we found the guy from the math problems.
Yes, good. I love it. Anyway, it's really unfortunate because the broader topic is modeling. What the hell do we most fundamentally want to use math for in the real world is to model shit. Do I want to go guess how many bags I need of fertilizer for my lawn, or do I want to do some basic math and go get a good estimate? Maybe get one more bag than an estimate just to be careful. In one sense, you could go, not get enough, or you could go buy too many, and the store's like, we don't take it back. And you're like, oh, shit. So the idea of modeling is huge, and it's unfortunate that it gets lost beneath this thing about the train heads north, like, the trains. Oh, God, with the trains. Okay. So, let's say I got 1,000 square feet of material. I'm going to do one of these problems from this worksheet that I did in the video. So I got 1,000 square feet of material to create a box, right? Now, there could be other considerations, but let's just say, for the sake of argument, that the only consideration I have is I want to be able to fit the most stuff in this box I create. So can you imagine, I really want you to understand, I want to create a box, a rectangular box. And it might end up being a cube, we don't know. And I'm going to say a little bit more than it said on the worksheet. Maybe you want to figure out what dimension should it be so that I get the most volume. Does that kind of make sense? And a real quick side note. Have you guys ever been past like a peanut farm or a corn farm? I'm from Georgia, so peanut farms are just the thing. You ever been at a farm? What are most silos in the shape of? Circular, right? Why? Why are they circular?
Like some kind of oyster or something like that, right? Like oyster to keep it like from, just something.
That's part of it, but the bigger reason is if you have a certain amount of material and you want to create the largest volume inside, a circle has a larger area. Therefore, if you multiply the circle, which is what a cylinder is, you get a larger volume inside. Now, why is some things rectangular like a moving truck? Because you're putting little cubes in the freaking thing, right? For the most part. Yes? So it depends on what you're throwing in there. So if you throw in little kernels, they're going to pretty much fill it up. Anyway, that's a little more than I wanted to say. So, I do know one thing about this. I wanted to have a square base. Good Lord, that's what that says. So all we know is it's got a square base. What does that mean? It's got a square base.
The sides are the same.
Sides are the same. So if I kind of draw a crappy little, I'm out of touch, out of practice. There you go. There's my crappy little thing. Poor little dude. I've created this guy. He's like, existence is pain. I'm going to erase you a bit more. So what are these going to be, obviously, then? What are these dimensions here? Or not obviously, but you can call them both.
X.
Whatever letter you use, you got to use. Now, can I put an X there?
No.
I just didn't know, but I shouldn't. Because there's nothing in the problem that says the height. It doesn't say it's a cube. It says it's got a square base. So I need another variable then, don't I?
Y.
Yeah, let's use y. Why? Will be different. It kind of makes sense. Now, what's the volume of this box? What's the volume of this box?
Length times height times
X
width.
squared.
X squared 1. I like it. That was beautiful synergy there. Length times height times width. X squared 1. What does this have to do with this problem? That's a physical constraint. What does that have to do with this?
It's a surface area.
X squared plus 1 must be less than or equal to.
No. It has nothing to do with volume, yes?
It's a surface area of the block.
Surface area. 1,000 square feet of material. The inside, I don't want any material in it, so I can put shit into it, yes? I don't want this to be that would be great because the luggage and you open it, it's just full. It's just, wait a minute, it's all plastic throughout. I can't put, what? This is just for decoration. All right. What the shit is the surface area? So I know the surface area.
2x squared plus 4xy.
Yes, y. So what is the area of this space? XY. And of course you have how many of those? 4. So you got 4 XYs. And then you got 2x squares, 11. Just make sure everybody else sees where it came from. And what I want from you right now is, can you write, what did I say exactly? Yes, write the volume as a function of x. Well, what do I have to do so I can write the volume? What is the volume currently a function of?
X.
Was x and y. Is y really anything it wants to be? Considering the whole problem? No, if it was anything it wants to be, why would it have to be 1,000 square feet total? So there is a constraint on y given what x is. I really want you to, so watch this. If I made the base too big, the height would be very small, correct? So I'd have something like, does this look like a good box? Do you have a box for moving? It's got a huge volume. Well, what do I do with this?
You could argue that actually it's a really small base and a really big height, it's just on the side.
Very true. But I won't. Now, so whatever these are, this will be affected by it. So y and x are not really independent of each other, right? Because of this constraint. All right, how are you guys feeling right now? You guys okay? Have we done anything too weird yet? Am I going too slow? No. You're like, I'm never going to say yes to that question. It's probably going to. Okay. So what I need is I need this as a function of x only. So I need to get rid of what? Not just get rid of it, I want to replace it. So what else do I know? What can I do with this?
Yeah, y by itself.
You can get y by itself. Right? You guys with me? So this is what I call the tell me, ask me problem. This is how I teach this in pre-calculus when you do the optimization problems. I don't know if you guys remember that. Pre-calculus where you had to set up an equation that became parabolic eventually, and you found the vertex, and that was the answer. Minimize the cost, maximize the profit, blah, blah, blah. Trying to make you little good capitalists. I love it.
Scrooge McDuck.
Uh-oh. Okay. So they told us this for sure. That leads me to one equation. And they asked me about something else. That's another equation. I want to use what they tell me in what they ask me because the number of variables is too damn high, right? I need to kill one of the variables, and I do it in a very subversive way. I substitute. So when you solve this for y, first off I can kill it too, is that cool? And then I can subtract x squared and divide by x. So again, what?
For the other side, that'd be 500x to the negative 1 minus x.
Yes, or that. Now the reason I left it like this, it doesn't really matter. Why did I do this? Why did we just do this? I forget.
Why?
And why did we need y? Look at it, good, good, okay. So volume is x squared times 500 minus x squared over x. One of the x's cancels. All right, so that's all I need for this problem. Now, just to kind of think to the future, doesn't this look like what's up? Like a negative cubic?
You forgot the 2 in the xy. You knocked out a 2, but there was still a 2 left.
All right, all right. So this would be over 2. All right. So this would look like a negative cubic, yes? Where would the, what do you want to call it? Where would, if I wanted to maximize this volume, where would that occur? If that, does everybody agree with me that that's a negative cube? Right? A cube would look like this. So a negative cube would look like this. Where would the maximum or minimum, depending on what the problem says, where would they occur? Now in this case, I want you to understand, this might be giving you some trouble. Can x be as big as it wants to be? No. Okay. So it's kind of limited as far as it can go. Where would the max and the min occur would be at one of these locations, yes? And what is happening there calculus-wise?
Zero.
What's zero?
The slope.
The slope is zero. So in chapter 4, we're going to take this equation, we're going to take its derivative, we're going to find where it equals 0, and see if that is a max or a min, right? Because that could be the location that would give us the largest volume. And that would tell us what the dimensions need to be. And one thing I've never done is take actual dimensions of like the average carry-on luggage and see how close it gets to the optimal possible dimensions, right? Anyway, so maybe we'll do that. You know, like, yay. Okay. The most important thing here is this was the modeling stage right here. In fact, the most important stage of the modeling was what the hell are your variables and how many do you need? The person that puts LWH, I feel bad for them because they skipped this and they have more variables than they're supposed to, and the problem is going to be basically impossible for them to do. So what's important here? What are the variables, right? How many do you need? What do they mean? And what are the equations for what the problem is telling you and asking you? That's basically what every word problem tries to do. It just does it in a really convoluted way. Okay. Let's see. Maybe I'll try to do one more of these. Everybody got what they want from this? Okay. Why my desk is so far away? Sorry. Oh, here's something interesting. That was a little too easy, but that's all right. Well, this is still interesting. So this is kind of silly, but again, like we just saw, x, y, z. The volume of this would be the area of the base times the height. That's what it is. And why does this make sense? Well, think of this as, you guys, have you ever heard in the historical period that there used to be these things called records? Does anyone still like records?
Talk about the big CDs, right?
Say again?
The big CDs.
They're like big CDs, exactly. Laser discs. That's even, it's still back in the day. I remember laser discs come out, we were like, oh my God, that's the future. So these, I was thinking this as like a record, and then I stacked a bunch of them up. Right, so the volume of this is the area of one record times how many are stacked up, which is the height. So what does that have to do with anything, Jeff? I don't freaking know. Oh yeah. Cylinder. Radius R, height H. What's the volume of the cylinder? What's the area of the base? Pi r squared. Times the height, right? Because isn't it a repeated shape? Isn't it like a bunch of coins stacked up on each other? Not Bitcoins, those are digital, but just coins. Stacked up on each other. That's the volume of a cylinder. Okay, I like it. So, this one's a little more straightforward. What if I had a cylinder? This is a little bit strange. Let me make a different problem than that one. I like it. Let me go one step further than this. What if I create, what if I cut this out, cut all this out, and make a cone? Can you guys see, it's like an upside down ice cream cone? Can you guys see that? I thought it did okay, but some of you guys are like, what shit is that supposed to be? That's a cone, yes? If you cut it out, take all that away, and you have a cone in the middle, you actually cut away 2/3 of the material. You're left with 1/3 of it. So the volume of a cone, that cylinder, Jeff, the volume of a cone is 1/3 the volume of a cylinder. All right, we're sort of becoming geometry class just for a minute, but real quick. Let's see if I can do this. I don't normally wow anybody with my drawing capabilities, but let's see what happens here. Even that's shitty as hell, right? Oh, let's see what happens. If I take every corner and go to one point and cut that out, what shape did I just make? Pyramid. What was the volume of the original? The volume of the rectangular solid, x, y, z. So what's the volume of the pyramid? 1/3. X, Y, Z. Always, anytime. And a cone is just the most basic pyramid. Believe it or not. Today you learned a lot. You're like, yeah, Jeff. But geometrically, a cone is the most basic pyramid. I don't know how you guys are feeling. They all right? So, what if I had I'm going to erase this, even though that's not bad. It's pretty good. All right. What if I had a stalagmite being formed? Right? Good old stalagmites. Everybody knows stalactites, so when the whole tight, the ceiling stalagmites down here. So when they drip, huh? Or sit on it. You gotta be careful. I like it. Don't play leapfrog over these stalagmites. And let's say that it's forming in a way such that the height is always 3 times the diameter. So that's just the way it forms. And you can look up, there's different cylinders. Different ones form different ways depending on what the material is that is being formed, the mineral, the whatever the stuff is. So the height is always 3 times the diameter. Okay. And we know the volume of a cone is 1/3 pi r squared h. Can you write volume as a function of radius only? No. Why not?
The diameter and radius.
I don't care. If you know the diameter, you know the radius, yes?
Yeah.
If the diameter circles 10, what's the radius?
5.
5. I don't even care what the units are, right? So try again.
Yes.
If h is 3d, and diameter is what related to radius?
1/2. Or no, 2.
Twice the radius. Twice. Why is it? I love this. Now it's pretty simple, right? I want volume as a function of radius only. Well, now you can replace h, you can replace it directly with 6r. 1/3 pi r squared times 6r. So that becomes 2 pi r cubed. For this cone, if I just measure the radius, I know the volume because we happen to know that this is always true. Then I can do shit with this, right? And it's going to be a lot easier to do stuff with this because there's less variables in there. Okay, now. This has all been a build-up, by the way. We haven't really gotten into the... Have you guys noticed much calculus yet? No. Okay. Just a little bit of a mention of calculus earlier. You guys feel semi-okay about this? So I wanted to let you guys remember substitution method, right? You guys remember matrices and all? Don't worry, we're not going to do matrices, right? We have elimination method, substitution method. Substitution method I always thought was very subversive, sort of like invasion of the body snatchers. You're like, bam. Right? Just kind of in the middle of the night, you go replace somebody. Okay. Now, when I write an equation, like, all right, let's say this. Let's start off with a nice easy one. Let's say there's a pond somewhere, and we're viewing it. I don't care. My drawing, I'm not going to try to say anything more. There's the pond, right? And we throw a rock into the pond. What's going to form?
Little circles.
Ripple, right? Circles. 11 concentric circles from the ripple from that, right? So we throw a rock in, and it kind of goes like this. Okay, that looks. Y'all know what it represents. So I'm curious, if I look at one of these circles, let's put our coordinate system so that that's the center. Wherever the rock goes in, that kind of makes sense. So I don't know if you guys even realize, in the real world, you could put a coordinate center wherever it makes the most sense. Yes, you could even turn it if it makes more sense. You're so used to putting shit on a coordinate system. In reality, we're taking a coordinate system and we're putting it on top of whatever we're looking at, right? So I'm going to take it and I'm going to put it, I'm going to put the center right there. So what's the equation of this circle? Now that I got a coordinate system down there, what's the equation of that circle?
Y plus x squared plus y squared.
Maybe. I heard some stuff. The equation of a circle. Equation of a circle. Okay, let's do this. Here's a circle. Pretend this is a circle. I'm going to pick any arbitrary point. Could that point have been there? Could it have been there? Would it be? What's the fundamental idea behind a circle? What's true about every single point on the circle? They're all the same distance from the center. Let me put an open circle there because it's not a point. 0, 0. What is this distance? What is that distance between those 2 points? You can do it. No. All I know is that's x, y, and that's 0, 0. That's all I know. What's the distance? Isn't it the hypotenuse of this triangle?
It's the root of x, it's root of y squared. X squared plus y squared.
Yes. So it's the square root of x squared plus y squared. Yes? Is everybody with me? Right? Yes, yes. And then I can square both sides. And then we can say, well, let's call this dude r, because that looks like diameter, and that's not a diameter, it's a radius. Let's call him r, and there you go. Okay, so that's the equation of the circle. Right? Now, my question is, if I know, do I even want to, let's keep going. That was a good little side note. What's the area of this circle? I don't want to, that's a little too early, but what's the area of this circle? Come on, what's the area of the circle? Pi r squared. Okay, thank you. All right, when we established the radiuses are? So what's the area of the circle then? Pi r squared. Okay, so area is pi r squared. Now, if I said the radius is growing at a rate of 2 inches per second. The radius is growing at a rate of 2 inches per second. That's pretty fast. 2 inches per minute is pretty slow. Let's say it's 10 inches per minute. 10 inches per minute. How fast is the area growing? Say again? So here's the problem. If I knew, I really want you guys, don't worry, I'm okay. I'm not even on any medications right now, believe it or not, just stay with me. If I knew the radius was 7 inches at some point, right? If we knew the radius was 7 inches, can we figure out what the area itself was? Shit, yeah. Easy as hell. What would you do? Why would we plug it in here? Why? That's a really dumb question. I don't care. Why would we plug it in there?
That's the variable you have.
That's the variable we have. You almost got it. That's the relationship between, this equation represents a relationship between the variables themselves, the physical dimensions that I'm talking about. I love you guys so much. This is asking me about rates of change. does this equation say shit about rates of change? Not yet. So if I knew the radius was 7 inches, I could just throw that in. And of course get what the area is. Because that's what that equation does. It relates the area to the radius. That's what that equation does. What do I need an equation that will do for me? I need an equation that will relate the rate of change of radius to the rate of change of area. Correct? So radius is growing at a rate of 10 inches per minute. How fast is area growing? That's the question. Okay, so here's where things get really nifty. If I asked you to take a derivative of this, you would probably tell me 2 pi r. And I wouldn't blame you, but that wouldn't be quite right. Because what am I going to take respect to? What am I going to take a derivative with respect to in this case? Look at my units. Yeah. I'm going to take a respect to time. Does time show up in this equation anywhere? No. So it's a third variable. Right? If I wait a certain amount of time, won't both of these change? If I wait until the radius is 8, the radius changed, yes? In fact, let's do this. If I wait a minute after I saw this, yes? If I wait 1 minute, what will the radius be now? 17 inches. Yes? And what would the area now be?
17 squared.
Yeah, pi times 17 squared, which is, I don't know. I used to know all these. 100 minus 120 plus 49, 350, 329? I don't know. I did that way too quickly in my fever head. Okay. I kind of want to know what that is, because what's 17 squared? 400 minus 120.
289.
Yeah, it's waiting on
289, okay. What I did wrong in my head. Real quick, what I'm trying to do in my head is 17 times 17 is 20 minus 3 times 20 minus 3. 400 minus 60 minus 60 plus 9. Oh, that's what I did wrong. Okay. I didn't just add 9, I added too much. All right. Let me stop for a minute. This still says nothing about the rate of change of things. I waited a minute and then everything changed. So the area is related to the radius, but what are both the area and radius dependent on? Time. That's kind of like a background variable, right? I love it. And the example I like to use, and I did this in the video, is Etch-a-Sketch. Hopefully, am I keeping you like crazy long? Did they update the clocks? Maybe. Etch-a-Sketch, when you, okay, real quick. Does everybody know what an Etch-a-Sketch is? Anybody not know what an Etch-a-Sketch is? All right. So next time, I used to have a little one on my keychain, and then I lost it somewhere, a little Etch-a-Sketch. But it's the things that they're orange, and you turn the dial, and the little thing on the screen moves around. Yes?
Toy Story, yeah.
Oh, Toy Story, yeah, Toy Story. There you go. Toy Story. I love it. There's a connection. I love it. There's a reference connection somewhere. If I turn one dial, so one dial is X direction, yes? And one dial is Y direction, yes? So if I want to go diagonally, I have to turn them both, don't I? If I change the rate of speed at which I turn one dial but not the other one, I'm going to curve. Yes? Of course, if I change the rate of speed the same, I'm still going to go in a straight line. Yeah, maybe. Maybe? Okay. So, now that one's a little bit trickier because X and Y are not related, but they're both related on time. But I kind of like that example. Now, I have an equation that relates area and radius. I just don't have an equation that relates rates. what would the units, no, not units, but what would the symbol be for this? Let me see if you guys, what does this represent the change of? What is radius? Change in radius per
Change in time.
time. That's what's so cool about this notation is you can see the units in it. So what are they asking me for? What notation want to use for this question?
dA over dt.
dA over dt. So I don't know what this is, but I do know that this is 10 inches. So if I just had a freaking equation that had dA dt and dr dt instead of just a and r, I could just plug shit in, couldn't I? I could just plug 10 in and be done with this damn thing. Jeff? Now let's see. I'm going to need one more piece of information. Hold on. I'm going to take this one. So let's try this. So what do you think I'm going to do with this equation then to make it into a form that helps me, that actually has these showing up in it?
Take its derivative.
Take its derivative with respect to time. So it's implicit differentiation. So I'll do this side. Oh man, okay, I'm done. Whew. Joke's just right. And what about the other side? What's the derivative of pi r squared with respect to time? What's the derivative of pi r squared?
2 pi r
2 pi r.
times dr over dt.
And just to remind you guys, just in case anybody's wondering why the shit, I really want this, now watch this, I don't know. I really, okay. If I took this with respect to radius, so if I took the derivative with respect to radius, right, this would be dA dr, and what would happen over here? Yeah, it'd be 2 pi r, and if you thought there was more, is dr. What is dr over dr? 1. I like it. And what's really neat, if I multiply by dt and then divide dr, don't I get this? All right, so there is a connection between these two. Love you guys so much. So now there's one more thing I have to know. Do I know this in the problem? Yes. And I want to know this, but I have to know this also. And that's interesting. That means the area is changing at a different rate depending on what the radius already is. So I'd have to tell you when the radius is 7 inches. So now do I have enough stuff to throw it into the equation? Yeah, I want to know what this is, so I don't know what it is. So, oh well. 2 pi, I need to know what r is. Yay. I need to know what dr dt is. Yay. I'm not going to put any units in it. Sure. So I get dA dt equals 140 pi inches squared per minute. And real quick, wasn't this 7 inches? If I put the units in, it isn't that inches per minute, so it would be inches squared per minute. But don't I know it's inches squared per minute because it's dA dt, inches squared minutes, right? And this is where I wish I had not erased what I just had. When r was 7, area was 49. When r was, we didn't do 8, let's do 8. When r is 8, area would be 64 pi. Oh, but if I wait, oh yeah, that's right, we did this correctly. We did r is 17. What was r, when r is 17, it was 280, 289. Now watch this, ready? This is inches and inches squared, blah, 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 blah. We just did this a second ago, right? This was, I waited 1 minute, and this is how things changed. The radius changed by 10 because I waited 1 minute. How much did the area change?
140.
Yes? But this is more work than I should have to do. I should just have find the equation. So I really want you to understand, all we're doing is we're taking a relationship between variables, taking a derivative, so now I have a relationship between rates of changes of those variables, which is what physics is, for example. Physics is all about flow rate versus whatever. It's all about comparing rates of change. Okay, let's see. Let's try one more. Is that time correct? Now's your chance, everybody.
Yeah.
Yes.
Yes, okay. If not, we'd be like, I don't even know what time it would be. All right, let me erase all this. So let's go back to the circle, dude. In a kind of a different way. Yeah, okay, let's do that one like that, sort of. No, not that one. All right, I'll make one up. Okay. So let's say, all right, let's say I'm at a dock. There's my dock. And there's a boat, going, oh yes, it's not a train, it's a boat. A boat going east at 10 miles an hour. And at the same time, there's a boat that, hello, there's a boat that takes off going north at 15 miles an hour. Pretty simple thing to draw. And I want to know how quickly is the distance between the boats. By the way, this is not on a lake, this is on an ocean, because I need a lot of room, because I'm going to let an hour go by, and they both will have crashed, possibly. How quickly is the distance between the boats changing after 1 hour? Oh, shit. This right here is what I call my snapshot. This is a snapshot. It goes through an hour. They're going to continue moving after that. So they're moving before that, they're moving after that. There's just an instant where I take a snapshot right at 1 hour. And then they keep going, right? So what I'm trying to say is, you don't want to bring in anything too specific too early. When I take derivatives, what happens to constants? They become 0, right? So if you put constants in too early, everything goes to 0 and you don't get any freaking answers. I need to capture the general relationship between things. So, what do you want to call this distance here for this boat?
What?
Holy shit. What about this distance? And what else should I put up there that the problem's interested in?
How about Leonard and Sheldon?
Too late. Yes, between them. What do you want to call that? All right, we'll call it H. All right, now, have I drawn anything that you don't think you could draw given this problem? Could you have come up with different variables?
Yes.
Yes. Would that have changed anything about your answer at the end? No. The variable themselves doesn't matter. They're called dummy variables because you're standing in place of things we don't know. Who cares what we call them? So part of what you're going to have to do is figure out what to use for what variables. What variables do you need? Will a picture help, right? Now, what's the relationship between these three things to begin with?
X squared plus y squared equals h squared.
Yeah, x squared plus y squared equals h squared. Exactly. Is h a constant? Hell no, because the further they get apart, the bigger h gets, right? So all three of these are not constants. Okay, now, there's a couple things to realize here, but what is it that I'm telling you? Oh, what is this here? So here's the next level of things. So this is the first level, is to draw, don't draw anything related to the snapshot yet. Capture the generalization of what's happening. You don't want to bring in too many constants yet, right? So there's the generalization of what's happening. You capture the relationship between those variables. And we understand that I'm going to eventually have to get a relationship between the rates of change, which is why the freaking section is called related rates. Now, can somebody tell me what symbol this should get based on our choices?
dx over dt.
Yeah, dx dt. That's how quickly the x direction is changing over time. So of course this is going to be, okay. And of course that means that the question is dh dt. I want to know what that is. Maybe. I really want this to be, we're using calculus to take something that relates variables themselves, and then we're creating an equation that relates rates. Because what can I do when I have an equation? I can just throw shit in. Can I throw this shit in to the equation I have at the moment? No, it's got nowhere to go. It's got nowhere to go, poor little thing. So of course, what do? What do I do this? Yeah. So what's the root of x squared with respect to t?
2x times dx over dt.
Good. Same thing here, right? And of course the same thing here. And the only real simplification I could do is to
I'll take out the 2's.
kill the 2's. Well, die. Well, you better die. Okay. All right. So now you stand back and make sure, okay, what is it that the question is asking you for? dh dt, right? That's the one it's going to have nothing that I know. What do I know? I know this, right? And I know this. What do I not know that I need to know?
X and y distance.
Yeah, I don't know x, I don't know y, I don't know h. Now, what are these from, though? I want this equation to tell me the answer at a specific moment. Now I bring the snapshot in. What moment are we talking about? 1 hour later. So after 1 hour, what is x? 10, right? 10 miles an hour, 1 hour later, 10 miles. What's y? 15. So what's h? Yes. Square root of 10 squared plus 15 squared. Pretty sure it's 225, right? 320, is that square root of 325?
Yeah.
Yes, okay, cool. Don't give me no decimals there, that's correct, that looks terrible. I'd be careful, because some of these problems get very difficult on the setting up stage of things. But the minute you have your equation and you take your derivatives, you find what you don't know and you throw them all in. So now we're at the stage where I just throw stuff in, right? So I get x, so I get 10 times dx dt, 10, plus y is 15, times dy dt is 15, equals h square root of 325, dh dt. And now you solve for dh dt. should get, well, I mean, this will be 100 plus, that's 325 again, right? The whole 325 divided by half of 325 is half of 325. And the units are going to be miles per. So there are a few stages to be aware of. There is information you don't want to bring in too soon. Because you can see, if I started putting constants in here, there would be zeros here. And I always have somebody that does that. And then they're like, I don't know where to go from here. I'm like, I don't know either. Okay. Maybe. Let me see. What time we got? Let's try one more. Let me see if I can give you one to try. Not too weird. That's a little weird. Oh, now that one's, well, all right. That one could be interesting. It's a little too much for this. Let's see. All right, I'm going to erase all this. Okay, so let's do a problem. This will be the last problem for the day, obviously. But it illustrates something that's going to happen to you a lot in your homework. Here's one again. So I have a water tank. That is how I say water. A water tank in the shape of an inverted cone. And let's say the tank itself is 4. Yeah, sure. We'll use. Yeah. My poor little tank has been through a lot. Okay, leave it alone. It's 4 meters tall and 2 meters in radius. I believe is what they're telling me, yes. Now start pouring H2O in. So I start pouring water in at a rate of, you just looked at it, Jeff, 2 cubic meters per minute. We stop with that. That's what the problem kind of puts out there. Find the rate at which the level of water is rising when the water is 3 meters deep. Oh shit. So.
It's 2 cubic meters per second, right?
Say again?
2 cubic meters per
Yeah,
second?
2 cubic meters per minute. How fast is water level rising when the water is 3 meters deep? Can somebody tell me real quick why the water would not rise at a constant rate?
Because it's a cone.
It's a cone, and as you go up, you have to fill more surface area, right? So it's gonna go up slower and slower as it goes up. I like it. So that's why they have to identify a certain depth. Now, what's missing in my picture? I've got my storage tank. Well, what have I been letting happen for a while? What am I doing? I'm pouring water into it, so what's missing in my picture there?
How much water?
Freaking water. So pick somewhere for it to be. Right? I guess we're going to. Be careful here. Here's where you gotta be careful. How tall is that? Too specific. Way too specific.
3 meters.
3 is the snapshot. 3 is what I want when I'm ready to put everything into my equation. I don't want that right now. I need to be able to, so I want an equation that will work no matter what the depth is. So I need to set up an equation where that is a variable, because that's changing over time. And then I'm going to put a 3 in eventually, right? But right now, I just want this to be whatever. So what do you want to call this? I heard H. And then what do you want to call this? Holy shit. Looks like I put 2 ones. So can somebody tell me, what is the volume of water?
One-third, five R squared.
Yeah, 1/3 pi r squared h. There's too many variables there. To be really, really honest, we could do it with those variables. It's not. Is there a relationship between r and h? There will be if I draw in. Pretend like this is straight. This is supposed to be right. Poor little thing. This is h, isn't it? And so I don't know how much you guys remember geometry. Thankfully, we're not going to use Pythagorean theorem because I don't know what the shit this is. But what kind of triangles are this one and this one? Similar triangles. So what's true about similar triangles?
Similar interior-angles.
No angles. Let's not bring, I really don't want to bring trig stuff into this. Right? So what's true about similar triangles? The height of the small dude. You can set it up several different ways. But the way I always do it to keep it straight, small dude to big dude, small height to big height is equal to small radius to big radius. This is going to happen to you often enough in the homework. You're going to want to look, you almost always want to try to find a right triangle somewhere, because either then, if it's about angles, you got trigonometry. If it's not about angles, you got maybe the similar triangles, maybe Pythagorean theorem, right? So in quite a few problems, you're trying to find triangles, right triangles, hopefully. Here it was similar triangles. So which variable would you rather solve for? And actually, it's kind of weird. Which variable do we have to solve for, which is a little bit evil? How fast is the water level rising when the water is 3 meters deep? What will this relate to? H. So what variable do we have to keep? H. So what variable do we get rid of? R. So solve for R. So H over 2. Right? Is that, do you guys understand what my motivation was there? Why couldn't I just pick one to get rid of? Because this tells me I have to have H around. Right? And it's asked me how fast is the water level rising. What is this in notation? How fast is the water level rising? What is this in the notation? That's how quickly what's changing, the water level rising. How quickly the height is changing. So I have H is 3, and they ask me DHCT. Obviously, I don't give a shit about R. Sorry, R. Too bad. Okay, so now I can rewrite volume as what? R is H over 2. Oh, you're the... This is a 3, by the way. Let me stop for a minute. Every problem is not going to be like this. You have to understand what motivated me to do what I did. Right? Because it's the same thing that should be motivating you to do what you're going to do. Simplify that for me. 2 squared. 4 times 3 is 12. H squared times H cubed. So now I have a direct relationship between volume and height. What can I do? I don't want that. That's not going to help me. Derivative. So I get dv dt. I did that side. What's that side? 3/12, so 1/4, right? The 3 comes down, 1/4 I, h squared times dh dt. I know h, I want to know dh dt, and what's this? 2. Yeah, I just didn't do that at the beginning. I should have identified this. How can I tell if dv dt is freaking volume meters cubed over time? I can tell it's dv dt, right? So now you just throw stuff in. It's almost too good to believe. This is kind of like, all right, related rates is not easy. I want you to, but it is not as hard as people seem to think it is. It really is just taking a known equation, doing calculus to it. Now I can throw rate information in because I did derivatives. I can throw rate information instead of just height and radius. I can throw changes in those things. So I have 2 equals 1/4 pi times 9, right? Times dht. And now I almost don't care. Now you just gotta divide, blah, blah, who cares? And that's plenty, I think, for today. Oh, shit. So don't forget, quiz first thing Friday. Test 2 is moved. On Friday, I'll have the practice test. I'll give that out to everybody. Next Monday will be review day, so I'll have the answer key for that practice test. Okay. Let me know if you have any questions. Otherwise, I will see you sometime. Hopefully Friday at least. Yeah, I don't know. I might see you right now.